Well, welcome. Thanks for making it. All my excuses for a misunderstanding. We had supposed that there was a bus at the hotel to get you here. So you all had your morning sports. Thank you for coming in time, nevertheless. So when we conceived this workshop, we had the idea that we should also invite people from the artificial intelligence community because we thought that the brain and the recent developments in AI would make sense and have also ethical issues, but we failed to recruit these people. Now, it just so happened that 2 weeks ago in this very same room, there was a large conference on quantum technology, quantum sensing, quantum computing, and all those people that we had asked for to come, they were there. And I happened to be there because I was interested in it. And so there were people from Microsoft and Google and IBM, but also a lot of quantum physicists from academia. And there were a few serendipitous events happening, and I would like to share them before we go on. First, it turned out that it will be a long way until quantum supremacy will really make its way. They have enormous problems with the error rate of qubits, and it's still an open question whether this can be scaled up to success, because they say that you would at least need 1,000 or more qubits entangled in order to really make use of quantum computing. But there was another interesting twist. Quite a number of physicists came up, and there has been a recent paper published by Google that showed very convincingly that one very important aspect of quantum computers, their advantage is to be able to compare a very, very large number of variables simultaneously and establish relations between them. That this function, which is in quantum computers realized by superimposition of wave functions, can actually be implemented one by one in networks of coupled oscillators. It's the same mathematics. The dynamics of these coupled oscillator networks are identical to the dynamics mathematically that are realized in these quantum computers. And so it just happened that, and I would like to show you this coincidence because it may be relevant also for this meeting. May I have the first slide, please? We have spent a couple of years now to simulate recurrent networks for quite different purposes. And here I have summarized the canonical features of a biological system. So we have neurons. Some of the neurons are pacemakers. They have oscillatory properties. We have microcircuits that have oscillatory properties. We have massive reciprocal connection between these nodes. There are feedback connections between the areas. So everything looks very much like a recurrent network, the nodes of which are functioning like damped harmonic oscillators. So we wondered whether this would buy us something, whether this would make a difference. So we simulated a network of this kind, columns that have the propensity to oscillate, that develop features and selectivity with experience, then recurrent connections, think of layer 3 in the cortex, that are endowed with Hebbian synapses so that the network can learn about statistical contingencies of features in the environment, generating an internal model of the world. So, and then we tested these networks in simulations, adding one by one ingredients that we knew existed in natural systems, and tested these networks on standard benchmark tests of handwritten letters or spoken words. And to our surprise, what we saw, and this is just a very few slides, this left graph shows the learning rate of recurrent networks as they are currently available. The green one is the famous LSTM that is incorporated in virtually all artificial intelligence systems, also in the deep convolution networks, to endow them with some memory function. Then in our network, we implemented leaky integrator. And this is the yellow curve. And see, they are better than what is on the market. And then the next step was to endow these nodes with the propensity to oscillate, to configure them as damped harmonic oscillators. And this improved the performance of these networks by orders of magnitude. The scale on the abscissa is a logarithmic scale, so this is learning steps, and then the ordinate is performance. So they outperform by orders of magnitude what's on the market in the moment, simply by reproducing what we know from cerebral cortex or hippocampus would be the same thing. Also, in terms of noise tolerance, these systems are extremely resilient. You see the depixel pictures in the top. What is on the market, the gated recurrent units and the long short-term memory, they are not very noise tolerant, while these coupled oscillator networks show very slow, graceful degradation with increasing noise. So that's surprising. So we started to implement more and more of biological findings. So we endowed the nodes with different preferred frequencies, which is the case in the cerebral cortex or hippocampus. Then we introduced production delays, made them heterogeneous, and then we allowed the recurrent connections to learn. And all this still improved further. What you see on this graph, the steep curve on the very left is the performance of a heterogeneous network of recurrently coupled oscillators. The second curve, which is not as good in learning, is the homogeneous network, and what is on the market is on the right side. So you see this enormous difference in performance of networks that are mimicking what we think is implemented in natural systems. So what do they do? As long as these networks are naive, this is the upper row of panels, these are correlation matrices of the activity of the nodes. They respond in a very boring, highly homogeneous way, a lot of synchronization everywhere. But when they learn, they start to evolve a very differentiated, complex landscape that is defined in phase space. Islands of synchrony being separated by islands of incoherence, and well, you see how these patterns look like. It's a very distributed pattern where the information is available like in a hologram virtually everywhere in this network. And this is how the elements respond. Some of them really look like responses as you get them in electrophysiological recordings. And when you do Fourier decomposition of all these oscillations, it's 1 over f, shows exactly the same as nervous tissue. So in these networks, cognitive objects, in our case it's letters and spoken words, they are very complex high-dimensional landscapes in phase space, and they are sculptured by interference. And with this, one can configure a virtually infinite number of different linearly separable landscapes in such networks, which is probably the reason for their superior performance. So what did we learn? We learned, and this was very much what these physicists told us would be the case, that the unique dynamics of coupled oscillators, they are the secret to boosting performance. Why? Because they extend the coding space by phase. Then they allow synchronization to occur, which facilitates the Hebbian learning because it maintains synchronous patterns over a sufficiently long period of time. And then there are phenomena that you don't see in any networks that lack oscillatory properties, which is resonance and entrainment. And this allows the network to oscillate and to propagate waves, traveling waves, and they allow the superposition of an interference of wave patterns, which is the gist of the superposition of wave functions in quantum systems. So mathematically, it is identical. So reasons for this stunning performance, it's the high dimensionality of the dynamic space. It's an analog computation. There is nothing digital in there. And it allows for the parallel search for the best match between sensory evidence and the stored priors, which are in these recurrent connections. And to our surprise, this annealing process resembles very much what happens in a quantum computer. There is a superposition of waves, and there is a sudden collapse when you measure or when you provide sensory evidence. And the only difference is that in quantum systems, they use spins, and if it so happens, in nervous systems, we would use the phase of oscillation. And mathematically, this is identical. So maybe, and this is something one has to explore in the future, natural systems got the trick of using analog computing strategies that resemble what a large part of quantum computers exploit, namely the superposition of wave functions. There's no entanglement, but the most important part of quantum computing can be realized in classical hardware. And so what are the consequences, and why did I put this up here? First, because unfortunately we didn't get these people here. I would have liked to hear them and challenge them. But you probably got the gist. It's a very holistic way of treating information, allowing you to compare simultaneously relations among many, many variables. And this is what brains can do so well. Think about the traveling salesman problem, or scene segmentation problems, or language parsing problems. These are things the brains can do very well, and quantum computers can do very well. And classical systems for Neumann architectures, deep learning networks, they have great difficulties with the traveling salesman problem or with the scene segmentation problem. So perhaps this has some relevance for our field. Maybe it suggests other readout strategies for brain-machine interfaces, because one can put more emphasis on face coding. Also, when one stimulates nervous tissue, perhaps this will help to produce more realistic stimulation paradigms. And then, of course, very attractive would be the implementation of this analog technology for neuroprosthetics, because these analog networks are extremely energy efficient. They can be miniaturized, and they work at room temperature, what quantum computers don't do. So with this, I would leave you, and then we go slowly into the formal presentations. But I thought this was an interesting coincidence, and I regret that we don't have these AI people here, because I think what they are doing now is of relevance to what we are doing. Thank you very much, and we'll hand over to Viviana, to Ed, who made it in time. Thank you. And I get the pointer down to you.